Impulse is when a force is applied for a period of time, usually a short period of time. And this force changes the momentum of the object. And like Newton's third law, there's actually always two objects, and each object will have an equal change in momentum but in the opposite direction. Now there are two ways to calculate impulse. Impulse, I stands for impulse, is an average force times the time. Or it's the change in momentum. It causes a change in momentum. Now the units for impulse are either Newton seconds, because you're taking a force times a time. Newtons are the units for force, times in seconds. Or you can have the same as momentum units, which are kilogram meter per second. So there's two possible units. They're actually the same thing, because when you break a Newton down into its pieces, it becomes this here in the blue circle. So those are two possible units for impulse. They're really the same thing if you break them down. Here's an example. A baseball bat hits a baseball. Once again, a lot of examples can be from sports, like a tennis racket hitting a tennis ball, a golf club hitting a golf ball, somebody's foot kicking a soccer ball. Usually when we're talking about impulse, we're talking about a force applied for a short period of time, changing the momentum of the smaller object to a more the momentum change of the smaller object will be the same as the big object, but you'll see a greater change in motion, acceleration for the smaller object, because the smaller object is more affected by the force involved. But here we have a baseball bat hitting a baseball. And let's say the baseball is traveling this way, and this is my not too bad of a diagram for a baseball bat. But the baseball bat's going to swing and hit the baseball. Baseball bat's going to go this way. It's going to apply a force of 4,000 newtons to the baseball for 30 seconds. So entry-level question here, just simple plug and chug. I equals the average force times the time. So impulse, the average force here applied is 4,000 newtons times a time of 0.30 seconds. So the impulse is 1,200 Newton seconds. That's not newtons per second, it's Newton seconds, newtons times seconds. That's the impulse applied to the ball. It's also the impulse applied to the bat. So here we have the baseball going towards the right. It will hit the bat. I haven't drawn the bat. It's not that important right here, right now. And the ball flies out towards the left. Now, we know that the impulse applied to the ball from the previous problem, the impulse was 1,200 kilograms meters per second, which is the same as the Newton second, same units, but I'm using some units that are now consistent with the momentum of 800 kilograms meters per second. I also know in this part now that the impulse changes the momentum, so the change in momentum is 1,200 kilograms meters per second. Now, let me explain the answer. You can look at this and figure out that the answer, the momentum, the final momentum, piece of F, is 400 kilograms meters per second. Now, how did I get that at 400? Because what you would think is that the final momentum is 2,000. Let me put down the wrong answer here and cross it off. You'd think the final momentum is 2,000. Now that would be the answer if it simply just sped up from 800 to 2,000 in the same direction. But it did not change. It did not speed up. You know, if a ball goes, if it's going 800 to the right, then it would have switched to 2,000 to the left. Then the delta P here would have been 2,800. Because 800 to the right, 2,000 to the left, it's like a positive and a negative. And I'm not putting in all the negatives here, but I'm just trying to do this conceptually. When you change directions like this is a huge change in momentum. It's kind of like two numbers on a number line. You have like an 800 positive to the right of 0 and then a 400 negative to the left of 0, and their difference, the spacing between them, the change is 1200. So these are not the answers. The answer is 400. That's a difference or a change of 1200. Now the batter swung and missed at this same ball. It was heading towards the right, and then the batter swings and misses, and the catcher catches the ball. So the final momentum in this case is 0 kilograms meters per second. The ball stops, gets caught by the catcher in the catcher's glove. The ball is no longer moving. So what's the impulse? Well, first of all, I can kind of do this problem backwards, but let's do it backwards. Part C says, what is the change in momentum for the ball while it's caught? Well, if it starts with 800 and gets caught by the catcher, the change in momentum, delta P, is 800. You could say it's negative 800. You don't need to. Kilograms meters per second. It was caught by the catcher. It changes momentum from 800 to 0. Well, therefore, the impulse that the catcher's mitt has on the ball is the same as its change in momentum. So I can go back to part A now. The impulse on the ball is 800 kilograms meters per second, because the impulse is just the change in momentum. And likewise, this problem is so easy it's hard. What's the impulse the ball has on the glove, on the mitt? Well, it's the same thing, because they have the same impulse on each other. So the impulse on the glove is 800 kilograms meters per second. So when something stops, finding the change in momentum is easier than when it actually changes directions, like the last problem we did or the next one I'm going to do here. Here's another ball. Sorry about my poor diagram here. Say it's a golf ball. Hits the floor and bounces up. It's the same ball on both sides of this diagram here. Just can't draw them on top of each other. So the ball's going down, hits the floor, and then bounces up. On the way down, it has a momentum of 12 kilograms meters per second. We want to find the change in momentum of the ball in part A here. Well, if you're going down with 12, that's your initial momentum, and then you rebound with 10 up, your delta P is not 2. Your delta P is 22 kilograms meters per second. Because 12 down and then 10 up is kind of like a negative and a positive. The 12, you could call it negative. It's like negative 12 on the number line and then positive 10 on the number line. The difference, the spacing between them would be 22 units of change, or distance, or change is what we really want to say here. Part B, what's the impulse on the ball? Well, the impulse on the ball is the same as the change in momentum. So the impulse is 22 kilograms meters per second. That's the impulse. All right, now we got to do part C. I'm going to go to the top over here. Part C, the impulse, well, the equation for impulse is the average force times the time. We know the impulse is 22. We're trying to find the force now, the average force, and the time is 375 milliseconds, which is 0.375 seconds. It's a point right there, because milli is divide by 1,000 to get your seconds, 0.375. So now if we solve for F average, the average force, it comes out to be 59 newtons of average force on a ball by the floor as it bounces. So one of the things that the book illustrates very nicely, and I am now going to emphasize, is that when things bounce, they generally have a bigger change in momentum than when things just simply stop. For example, this golf ball had a change in momentum of 22 kilograms meters per second. If this would have just been like a wad of clay that hit the ground and stuck to the ground, its change in momentum would simply have been 12. It would have gone from 12 units of momentum to 0 units of momentum. Kind of like the previous problems we did with the baseball. If you just simply catch a baseball, whatever momentum it had, it loses. That's its change in momentum. But if you hit a baseball or a golf balls usually don't bounce. They're usually starting from a 0 momentum. But a tennis ball coming into your racket and bouncing back out off the racket, that's a big change in momentum. Big changes in the momentum are the ones that are bouncing. And those are sometimes associated with even bigger forces as opposed to something that's just required to stop. So we'll keep that in mind when we answer some questions from the book.